This video is not really about acoustics so much as it is about two-channel stereo reproduction systems and how you perceive the image location from left to right. To start, I'll say that I'm assuming that you're listening to this video using a pair of loudspeakers that have been correctly configured. This means that the triangle formed by you and the two loudspeakers has three sides with identical lengths. If you're listening with headphones, then some of the statements I'll make later won't be very accurate, but I'll deal with those as we go along. If you're listening to this video using anything else, I'd recommend that you press pause and connect to a real output. Let's talk a little about how you hear the direction to a sound source, which means that we're only going to talk about a portion of one dimension. In this video, I'm not going to talk about how we perceive the height or the distance to a source. This means that we're only talking about the angle to the source and only in the front. If you have a thing making a sound out there on the horizon somewhere, the sound arrives at your two ears. If the source is directly in front of you and everything is theoretically perfect, then the sound at your two ears will be identical and you'll hear the source directly in front of you. If the source moves to the right, then generally speaking, the sound will arrive at your right ear earlier and louder when compared to your left ear. If the source moves to the left, then the left ear gets the louder, earlier sound. Of course, everything is much more detailed and complicated than that, but we're not going to go any further into this topic than what I just said. If you have a decent two-channel stereo playback system, meaning you either have a good pair of headphones on or you have two loudspeakers in the room, then we can use these two aspects of the sound to simulate a position of the sound source. Right now, you're listening to my voice, which has been recorded as two identical audio channels. That means that the left and the right audio channels are exactly the same level, and there's no time difference between them. People who work in the audio industry will say that there's no interchannel amplitude difference and no interchannel time difference, which is just an expensive way to say that the two audio channels have the same content. At the moment, you're listening to a sound, which is my voice, in both loudspeakers at exactly the same level and exactly the same time. And you're going to hear that source directly in front of you in the center between the two loudspeakers. An audio geek like me will say that the phantom image of my voice is in the center, or they'll also talk about a phantom center. If you don't hear me as a phantom center, then this means that either one loudspeaker is louder than the other, or their two signals are not arriving at the listening position at the same time, probably because they're not the same distance to you, because you're probably not sitting in the middle. But I'll assume that you've done everything correctly, and so you hear my voice directly in front in the center. Of course, if you're listening under headphones, then it'll be different. Then my voice will probably sound like it's in the middle of your head. Let's now make one channel louder than the other. I've just changed things so my voice is now 2.5 decibels louder in the right channel than it is in the left channel without changing the time delay difference. So now you should hear my voice slightly to the right of center. Actually, it should have moved about 1/3 of the distance to the right loudspeaker. So if your loudspeakers are configured correctly, my voice has moved about 10 degrees to the right because that right loudspeaker is out at 30 degrees. If you're listening under headphones, then I probably moved more than 1/3 of the distance to your right ear. That's because we're more sensitive to interchannel amplitude differences and interchannel time differences in headphones because there's no leakage across your head to the wrong ears. Note that an audio geek will say that my voice is now panned to the right. The word pan is shortened from a device that was used to adjust the interchannel amplitude differences in a two-channel recording, and that device was called a panoramic potentiometer, but that's too long to say, so it was shortened to pan pot, and that was used to pan the phantom image to the desired location. Now I've increased the interchannel amplitude difference so that I'm 5.5 decibels louder in the right channel. The result should be that I've now moved about 2/3 of the distance to the right loudspeaker, or to an angle of 20 degrees in a correctly set up stereo system. Now I'm 15 decibels louder in the right channel than I am in the left. You might notice that I haven't really gotten louder overall, and this is because I've increased the level in the right loudspeaker a little, and I've turned down the left loudspeaker by a lot. The important thing to remember here is not the absolute levels of the loudspeakers, it's how loudly they're playing relative to each other. My voice probably now appears to be in the same location as the right loudspeaker, at an angle of about 30 degrees. Remember that the left loudspeaker is still playing, it's just 15 decibels quieter than the right loudspeaker. If I completely mute the left loudspeaker, then things will sound different. This is with the left channel completely muted. This is with it playing 15 decibels quieter than the right loudspeaker. This is with the left channel completely muted, and this is with it playing 15 decibels quieter than the right loudspeaker. Now I'm back in the center, therefore with an interchannel amplitude difference of 0 decibels and an interchannel time difference of 0 seconds. Now I'll do the same trick again. I'm going to play with the phantom image location of my voice, but now I'm not going to change the levels of the two loudspeakers. I'm only going to change the relative time delay. So now I've delayed the left channel by 220 millionths of a second, or 220 microseconds. And you can probably hear that I've moved about 1/3 of the distance towards the right loudspeaker again. It might be a bit of a surprise to know that such a small change in time results in such an audible effect. What we're doing by delaying the left loudspeaker by 220 microseconds is the same as just moving it 7.6 centimeters further away, because sound travels at 344 meters per second, and 0.00022 times 344 is 76 millimeters. In other words, if you set up your stereo loudspeaker pair and you make a 7 centimeter error in the distance to one of your loudspeakers, then the image won't only not be in the center, it's going to be moved 1/3 of the distance to the closer loudspeaker. Now I've increased the interchannel time difference by delaying the left channel by 440 microseconds, or 440 millionths of a second. So this is equivalent to having moved the left loudspeaker about 15 centimeters further away. And I'd estimate now that you'd hear my voice coming from a location about 2/3 of the distance to the right loudspeaker, or at an angle of 20 degrees. Remember that the level of the two channels is still identical. I'm only playing with the delay of the left channel. Now I've increased the interchannel time difference by delaying the left channel by 1.12 milliseconds, or 1.12 thousandths of a second. This is the same as moving the left loudspeaker about 38 centimeters further away than the right loudspeaker. So at the moment, I'd guess that you can hear my voice coming from the right loudspeaker. So when the two audio channels have exactly the same level, a time difference of about 1 millisecond is enough to move a source from the center to one of the loudspeakers. Now I've moved back to the center, so my interchannel amplitude difference is 0 decibels and my interchannel time difference is 0 milliseconds. You probably noticed that a phantom image location that has been panned by changing the interchannel amplitude sounds different than when I was panning using an interchannel time difference. For example, this is an image that has been moved using interchannel amplitude differences. This is an image that has been moved to about the same place using interchannel time differences. This is an image that has been moved using interchannel amplitude differences. And this is an image that has been moved to about the same place using interchannel time differences. There are a number of reasons for this difference in the sound, and I hope to be talking about those in a future video. In addition, it's possible to use interchannel amplitude differences and interchannel time differences in combination, so I could make the sound of my voice a little quieter and a little later in the left channel to push the image towards the right loudspeaker. I'm not going to demonstrate this because the total number of possible combinations is infinite and there are restrictions on how long this video can be. However, I will make one quick demo. Right now you're hearing my voice 15 decibels louder in the left channel, which should push the image all the way into the left loudspeaker. But at the same time, I'm 1.12 milliseconds earlier in the right channel, which should push my voice in the opposite direction. The question now is, where do you hear my voice? And chances are you're experiencing one of two things. One possibility is that you just hear my voice in the right channel, because generally speaking, interchannel time differences win over interchannel amplitude differences. The other possibility, which is more likely, is that you're hearing my voice pull apart in space, with some frequency bands pulling to the left and other frequency bands pulling to the right. Either way, if you have a conflict between the interchannel amplitude difference information and the interchannel time difference information, then your imaging will suffer. This is a good thing to remember if you're a recording engineer. For example, if you're recording a drum kit, you typically put a mic on each drum, and then you set up 2 overhead mics above the kit, primarily to capture the cymbals. And those mics are usually spaced apart, which means that there's going to be delay differences on the time of arrival of the drums in those mics. If you solo the overhead mics and you listen to the snare drum, it'll have some image location between the loudspeakers. But if the snare drum mic is panned using interchannel amplitude differences to a different location, then you get a conflict between those two pieces of information, similar to the conflict that you're listening to right now. In other words, the interchannel amplitude differences are telling you the snare drum is in one place, but the interchannel time differences from the overhead mics are telling you that it's in a different place. This means that you should pay attention to the locations of all the drums in the overheads and then pan your individual drum mics to match those locations to clean up the mix. From here to the end of the video, I'll just go through 10 panning locations in case you want to use this for testing loudspeaker or headphone systems. Stereo phantom center. The interchannel amplitude difference is 0 decibels and the interchannel time difference is 0 milliseconds. The image should appear to be positioned in the center of the 2 loudspeakers, directly in front of you. Interchannel amplitude panning, 10 degrees left. The left channel is 2.5 decibels louder than the right channel, and the interchannel time difference is 0. The image should appear to be positioned 10 degrees to the left of center, or 1/3 of the distance from the center to the left loudspeaker. Interchannel amplitude panning, 20 degrees left. The left channel is 5.5 decibels louder than the right channel, and they have an interchannel time difference of 0. The image should appear to be positioned 20 degrees to the left of center, or 2/3 of the distance from the center to the left loudspeaker. Interchannel amplitude panning, 30 degrees left. The left channel is now 15 decibels louder than the right channel, and the interchannel time difference is 0. The image should appear to be positioned 30 degrees to the left of center, or in the left loudspeaker. Interchannel amplitude panning, 10 degrees right. The right channel is now 2.5 decibels louder than the left channel, and the interchannel time difference is 0. The image should appear to be positioned 10 degrees to the right of center, or 1/3 of the distance from the center to the right loudspeaker. Interchannel amplitude panning, 20 degrees right. The right channel is now 5.5 decibels louder than the left channel, and the interchannel time difference is 0. The image should appear to be positioned 20 degrees to the right of center, or 2/3 of the distance from the center to the right loudspeaker. Interchannel amplitude panning, 30 degrees right. The right channel is now 15 decibels louder than the left channel, and the interchannel time difference is 0. The image should appear to be positioned 30 degrees to the right of center, or in the right loudspeaker. Stereo phantom center. The interchannel amplitude difference is 0 decibels, and the interchannel time difference is 0 milliseconds. The image should appear to be positioned in the center of the 2 loudspeakers, directly in front of you. Interchannel delay panning, 10 degrees left. The interchannel amplitude difference is 0 decibels, and the right channel is delayed relative to the left channel by 220 microseconds. The image should appear to be positioned 10 degrees to the left of center, or 1/3 of the distance from the center to the left loudspeaker. Interchannel delay panning, 20 degrees left. The interchannel amplitude difference is 0 decibels, and the right channel is delayed relative to the left channel by 440 microseconds. The image should appear to be positioned 20 degrees to the left of center, or 2/3 of the distance from the center to the left loudspeaker. Interchannel delay panning, 30 degrees left. The interchannel amplitude difference is 0 decibels, and the right channel is delayed relative to the left channel by 1.12 milliseconds. The image should appear to be positioned 30 degrees to the left of center or in the left loudspeaker. Interchannel delay panning, 10 degrees right. The interchannel amplitude difference is 0 decibels, and the left channel is delayed relative to the right channel by 220 microseconds. The image should appear to be positioned 10 degrees to the right of center, or 1/3 of the distance from the center to the right loudspeaker. Interchannel delay panning, 20 degrees right. The interchannel amplitude difference is 0 decibels, and the left channel is delayed relative to the right channel by 440 microseconds. The image should appear to be positioned 20 degrees to the right of center, or 2/3 of the distance from the center to the right loudspeaker. Interchannel delay panning, 30 degrees right. The interchannel amplitude difference is 0 decibels, and the left channel is delayed relative to the right channel by 1.12 milliseconds. The image should appear to be positioned 30 degrees to the right of center, or in the right loudspeaker.